Hello, my name is Christina Aragon, and I'm a PhD student at Oregon State University. Today I'm going to be talking about assimilation of citizen science data to improve modeled estimates of snow distribution in remote data-limited environments. I would like to acknowledge my co-authors, David Hill, Emilio Mayorga, Anthony Arendt, Gabriel Wolkin, Ryan Crumley, Katrine Wilkstrom-Jones, and Elizabeth Burkowski. This presentation will cover three main topics. I will first introduce the Community Snow Observations Citizen Science Snow Depth Dataset. Then I will give an overview of our modeling workflow. And finally, we will look at a case study where citizen science data is assimilated into a physically based snow model. Water storage as seasonal snow plays a key role in the hydrologic cycle. In mountainous regions across the globe, water storage as snow fundamentally links together atmospheric, hydrological, ecological, and human systems. Despite the importance of seasonal snow, we are limited in the number of in situ snow depth observations available in mountainous regions. The lack of in situ data available in high elevation complex terrain motivated the creation of the Community Snow Observations, or CSO, project. CSO was launched in 2017 with the goal of developing a global network of citizen scientists who would collect and submit measurements of snow depth. While anyone can participate, the project has prioritized participation by backcountry recreationalists and snow professionals. These users have been prioritized since they frequent high elevation regions of complex terrain where there are few data sources for in situ observations. Participation in CSO is easy. There are only 3 simple steps. First, participants will go somewhere in the backcountry. Second, participants measure the snow depth. This is typically done with an avalanche probe, since this is a safety tool already carried by backcountry users. And third, participants submit their snow depth measurements via a mobile app such as Mountain Hub, sitsci.org, or regobs. Each of these apps geolocate the submission when participants enter the snow depth. Participants are also able to share observations through SnowPilot, which is a desktop platform commonly used by avalanche professionals. All CSO data are publicly available for download at the communitysnowobs.org website or through an API. CSO observations are unique in that they increase the diversity of the terrain where snow observations are taken. Here, we compared the terrain features associated with the locations of CSO observations and SNOTEL stations in the western United States. We extracted terrain features for CSO and SNOTEL locations from the 10-meter resolution National Elevation Dataset. Looking at the elevation distributions in the upper left plot, CSO provides a notable number of observations at high elevations, many of which are higher than the highest SNOTEL stations. The distributions of slope are shown in the plot in the upper right corner. Slope was computed using the 4 connected neighbors of each pixel corresponding to the location of the CSO observation or SNOTEL site. The majority of CSO observations are taken on terrain with higher slope angles than the SNOTEL stations. We also computed a terrain complexity metric for each observation. The terrain complexity metric was calculated as the standard deviation of the 3x3 square kernel surrounding an observation location. Terrain complexity for CSO and SNOTEL data are shown in the bottom plot. CSO observations are largely located in more complex terrain than SNOTEL stations. Overall, we see that CSO observations could supplement other established in situ snow data sources such as SNOTEL. Now we are going to take a look at how CSO data and other in situ snow depth observations compare to the Snow Data Assimilation System, or SNODAS. SNODAS provides daily gridded information on snow variables over the United States. The SNODAS modeling system assimilates in a wide variety of information, including SNOTEL, snow course data, CocoRa's data, and others. These plots show the density functions of the errors between the SNODAS estimates of snow depth and the observation. Error is defined as the SNODAS estimate minus the observation. In each case, a nearest neighbor approach was used to extract the SNODAS value corresponding to the measurement location. For the CocoRa's, snow course, and SNOTEL datasets, these errors are normally distributed with no bias. This is expected since those datasets are assimilated into the SNODAS modeling workflow. The results for the CSO dataset are different. There is a significant negative bias indicating that the SNODAS model is underpredicting the snow in high mountain complex areas visited by CSO participants. Now that we have seen the potential utility of CSO data, we are going to switch gears and talk about the CSO modeling structure and workflow. Many snow modeling efforts are intensive catchment-style campaigns where the watershed is heavily instrumented with sensors that provide data about weather and snowpack. The CSO project vision is different. We've adopted a data-driven, unstructured approach that is based on where citizen scientists decide to travel and measure snow. We welcome the anytime, anyplace procedure to data collection by participants. The modeling structure is illustrated here. We use Liston and Elder's Micromet and Snow model. Micromet distributes weather forcing data to a high-resolution model grid, and Snow model is a physically based snow evolution model. SNOASIM by Liston and Heemstra integrates with Micromet and Snow model and is used to assimilate CSO data into the models. This modeling structure fits into a larger modeling workflow. To rapidly launch new model domains, we have developed freely available scripts and notebooks that fully automate the acquisition of weather, terrain, and land cover data for a prescribed bounding box and time period. We also have scripts and notebooks to obtain SNOTEL and scan weather and snowpack data for the purposes of calibration and evaluation, and we can automatically calibrate each of our model domains. We currently have 6 modeling domains in the Western United States. These are indicated by the red boxes in the figure to the left. Snow model runs are calibrated to the SNOTEL stations located in each domain. A sensitivity analysis was completed to determine the target parameters for calibration. Each calibration tests over 10,000 combinations of model parameters. Each snow model calibration run is evaluated based on R-squared, MBE, RMSE, NSE, and KGE. In our current workflow, we are using the Nash-Sutcliffe Model Efficiency Coefficient, or NSE, to select our top calibration parameters. Assimilation is the third part of our modeling workflow. As an initial step, all snow depth measurements are converted to SWE estimates using the freely available regression methods described in Hill et al. 2020. The Hill et al. Regression approach is a recent improvement over other regression methods such as Pistocchi 2016 and Sturm et al. 2010. Once the CSO snow depths have been converted to SWE, we assimilate in the data collected from citizen scientists. In SNOASIM, the assimilated SWE is compared to the model SWE estimate, and a correction surface is created that adjusts precipitation inputs and/or melt output rates in order to guide the model simulations back towards the assimilated value. We are still in the process of optimizing the assimilation procedures, so the rest of this talk is going to focus on an assimilation case study from our Wyoming modeling domain. This is domain number 4 on the image to the left. This animation shows a SWE evolution from the best calibration run in the Wyoming modeling domain. The Wyoming domain is located in the heart of the Rocky Mountains and spans the headwaters of 3 U.S. water basins: the Pacific Northwest Basin, the Upper Colorado River Basin, and the Missouri River Basin. This domain is 1,382 by 2,476 pixels with a resolution of 100 meters per pixel. We are going to be focusing on the water year 2019. In the water year 2019, there were 28 SNOTEL stations and 310 CSO observations in this domain. Earlier in this talk, we pointed out that CSO observations are unique in that they provide a source of in situ data in complex terrain where we typically lack observations. Here we are going to explore how assimilation of CSO observations with high terrain complexity scores may enhance our models of snow distribution in mountainous regions. We will do this with 3 modeling scenarios. 1, we have a baseline snow model run using the parameters from the best performing calibration run. 2, we will divide the SNOTEL stations in half and assimilate half of the stations and use the other half of the stations for evaluation of our modeling scenarios. The yellow dots on the map above indicate the SNOTEL stations used for assimilation, and the green dots indicate the SNOTEL stations used for evaluation. The third modeling scenario will assimilate CSO observations. The CSO observations that fall into the top quartile of terrain complexity scores are used for this assimilation case study. The CSO observations used for assimilation are indicated by the red plus signs. Notice that these observations are largely located in the center of the domain in the Teton Range. Here we show the SWE time series at 4 of the 14 evaluation SNOTEL sites. The observations at each SNOTEL site are shown in light blue. The baseline snow model scenario is shown in dark blue, the SNOTEL assimilation scenario is shown in yellow, and the CSO assimilation scenario is shown in gray. The NSE score of the baseline SNOTEL and CSO assimilation runs are given above each plot. These plots provide a variety of performances for the various modeling scenarios. For example, the upper left plot shows very similar performance between the assimilation scenarios, while the lower left plot shows similar performance between all three modeling scenarios. The upper right plot is a case where the CSO assimilation scenario outperforms the SNOTEL assimilation, and the lower right shows a case where the SNOTEL assimilation outperforms all other scenarios. Overall, the performance of the CSO and SNOTEL assimilation scenarios are remarkably comparable. Modeled SWE is improved at 79% of the evaluation sites when CSO data are assimilated compared to the baseline snow model scenario, and modeled SWE is improved at 86% of the evaluation sites when SNOTEL data are assimilated. This is really impressive considering that the SNOTEL scenario was assimilating daily SWE observations, while CSO observations were contributed opportunistically by citizen scientists and are relatively random in space and time. We can use this modeling output to explore the implications of CSO data assimilation on the regional modeling of annual snow water storage. The dashed line in the plot above shows an example SWE curve. The snow water storage is the integral of the SWE curve, or the area under the curve which is shaded. The snow water storage metric can help us link CSO observations to water resources at an annual scale. These plots show us how each modeling scenario results in different projections of annual snow water storage. The plot on the left shows the difference in storage between the SNOTEL assimilation and baseline scenarios. The plot in the center shows the difference between CSO assimilation and baseline scenarios, and the plot on the right shows the difference between the CSO and SNOTEL assimilation scenarios. Both assimilation scenarios result in higher annual snow water storage than the baseline snow model scenario. Looking at the plot on the right, the CSO assimilation scenario results in higher annual snow water storage than the SNOTEL assimilation scenario through the middle of the modeling domain. Recall that this is the region where the majority of our complex terrain CSO observations were located. In this right plot, we also see that the CSO assimilation scenario has lower annual snow water storage in the northwest near Yellowstone and in the southwest around the Wyoming Range. CSO observations were missing from these areas. Future work will address this by assimilating sets of CSO observations with broader spatial coverage throughout the domain. These differences in annual snow water storage could have implications for agricultural and municipal water resources, reservoir operations, and hazard mitigation. The CSO project provides a unique source for in situ SNODAP data. CSO observations supplement existing in situ data by providing observations on the landscape where in situ data is typically lacking. With our data-driven approach, the CSO project can implement model simulations in areas where citizen scientist participation is high and where calibration data exists. Our preliminary results suggest that the large CSO dataset may be of value to regional to national scale assimilative modeling efforts. Up next, we will finish CSO assimilation optimization and open source workflows. We are also aiming to provide nowcasts of snow distribution in our modeling domains. Thank you for listening. If you would like to contribute observations to our project, visit our website, communitysnowobs.org, for detailed tutorials on how to get involved. Stay connected with our project by signing up for our mailing list on the website or check us out on Twitter, Instagram, or GitHub.